Okay, so as we're continuing on with our rotational motion section here, rotational kinetic energy is another important thing to get. I kind of lied to you guys before. I told you that total work, total energy, right? Total energy, energy total was equal to potential energy plus kinetic energy plus any work that was done on the system, right? So if this thing wants to move, right? Well, right now it's got potential energy, right? If I throw it up into the air or down, it'll also have speed. So I'll have kinetic energy. And if I want to change anything about that, right? If I want to take and make sure it doesn't fall to the ground, I can do that, but I've got to pump work into the system by holding it up, say, right? So I've got to do something to raise it if I want to increase my potential energy. So those three things were our total energy package that we talked about before, except it's a lie. I know, I keep doing that to you guys, right? There's one thing I lied about. There's one other piece, okay? And it is rotational kinetic energy. So it's actually kind of a piece of this. So we'll talk about it a little bit. So here it is. Okay, so what is rotational kinetic energy? You guys have seen rotational kinetic energy a lot. Actually, you've seen it a whole lot and you didn't realize it. If you ever see those maple tree seeds, those little helicopters, as they fall down, they kind of spin around faster and faster as they fall. They're actually turning some of that potential energy through work, right, with friction with the air drag. They're actually making the thing spin faster and faster. So they're gaining a speed, even though they're not actually going faster this way or flying up into the air or falling down, right? They're spinning faster and faster, so they're actually getting more energy. You do it with your bike as well. If you have a wheel, right, you start out and it's not moving at all. And it takes work from you cranking on that pedal. You have to do work, right? But the only thing that happens at first is the thing starts to spin, especially if you've got your bike in the air, right? If you're working on it and trying to like drew the wheel or something like that, you can spin that tire by doing work on it. But according to this, well, we haven't raised it up into the air. We haven't thrown the wheel, right? So it was actually not getting any energy into it? Well, yeah, it was through rotational kinetic energy. So the way that this works, okay, is think about this. You got little blocks of mass out here, okay? So in fact, let's talk about this. This is a mass on the end of a stick, right? So what I can do is I can take that mass and I can rotate it. And when I do, you can see that how much mass is on the end of this is really it's gonna determine how much energy it takes to move the thing. Right? And also how much energy I give it is going to determine how fast it starts going. Give a lot of energy, it starts spinning fast. Tiny little bit of energy and it just barely moves. Right? So, rotational kinetic energy has everything to do with this mass. But as we found out with torque, that mass also has something going on with the radius, the distance away from the center point. Right? So what we have to do is we have to, for rotational kinetic energy, only talking about the rotational part of kinetic energy, okay, for rotational kinetic energy, the things that we have to take into consideration, well, let me back up. What we want to talk about is it's just kinetic energy, isn't it? I mean, this is still a ball flying around. It's just flying around in a really predictable way, right? So we've still got our kinetic energy formula, 1/2 mv squared. Right? No big deal. We're going to still use this. This is still true for this, but we got to modify it because when we have a speed on this, it's something it's a speed that is actually, that velocity is changing direction all the time, so the velocity is constantly changing, so that's not going to work terribly well, changing direction all the time. So what we have, though, is a very stable thing. It's going the same path the whole time. So really what we're talking about here is somehow we're going to have to put in an omega in place of that v. But we can't just swap them out because v is not equal to omega. But if you remember during the mousetrap car project, okay, v was equal to omega times the radius, the distance away from your center point, your pivot point, right? So what we have is a circle, something going around in a circle like that. Here's our linear velocity, okay? But what we need is an angular velocity. So the way that we determine that is by figuring out this velocity is entirely dependent on how far out it is on the radius, okay? So your velocity here will be very different than your velocity here, because your radius has something to do with it. But this, your angular speed, doesn't matter at all where you're at on that circle. In fact, if you take this and move it, right, so here's this point here, this wheel, go ahead and put a stripe on it so you can see that maybe a little better. That thing, the whole length of it is actually going the same number of radians around that circle every second. It's not changing, it's very stable. So, to put that in, we have to turn this equation into one that has an omega in it. And the way we do it is by substituting. I know you all love substitution, right? So we're going to substitute this business right here in for our V, okay? So for rotational kinetic energy, okay, we have 1/2, mass still exists, that didn't go away, but instead of V, I'm going to put in omega times R, or omega times our radius. And in fact, I know, you guys like when that radius is a lowercase r, right? That's what you're familiar with. Omega times radius, okay? But remember, our V was squared, so this whole business also has to be squared. So let me rewrite that, okay? Let's simplify this all down, instead of having a bunch of stuff in parentheses. So we still have 1/2 m, and instead of this, each thing in there gets squared. So we have times omega squared times r squared, okay? So that right there is your rotational kinetic energy formula. Except this can be kind of awkward, and it's already going to be kind of a longer thing, right? So what we're going to do instead is we are going to take and simplify this down more, okay? And how we do that, this is a weird thing. We need to substitute something in for the mass here, because this mass is still living in a linear world, okay? We need an equivalent, and a rotational equivalent of mass. And it turns out that you already know what this is. This is strange, okay? But the tendency of this circle, right, this mass, to want to change direction, well, you remember what that was? Everything wants to keep going in a straight line at the same speed forever. Newton's first law, right? Unless acted upon by a force. We've got a centripetal acceleration, that acceleration towards the center that's constantly changing the vector, right? Changing the direction that ball is going. So, we need a rotational version of mass that actually doesn't care that it's spinning around, something that's stable now. So, it turns out the rotational equivalent of mass is actually inertia. Okay, so on that wheel that's going around like this, you have a block out here, that's your mass. It matters how far out that mass is, right, your radius, because that'll give you a torque, all right? So, to take that into account, we need to figure out how far away it is from the center, and we need to figure out how much mass is out there, and those two things will actually figure out how hard it is to move it, okay? How much inertia it takes to move that mass to change its speed or anything else. So, it turns out we need to get the mass and the radius together then, so that they are detailing exactly how that mass is moving as the wheel spins, all right? So let's reorganize this whole thing, okay? So rotational kinetic energy has something to do with a 1/2, which we don't care about, it's just a number, okay? Has something to do with that angular speed, which again we care about but not a whole lot right now. But we need to get that mass and that radius together. So now we got a new term, okay? Mass times radius squared, it turns out, and again, I apologize, if you need any of this information, come back and review the video. I only got so much whiteboard space here, okay? So let me make a little room over here. Tiny, tiny little bit of room, okay? So, the term oh my goodness, M, needed more of a thing to wipe this down to dry it off. Okay, so M times R squared is actually our moment of inertia, and there's our new term. mr squared is a moment of inertia. And that moment of inertia is actually a sum. If I have a wheel like this, right, I don't just have one mass here, I actually have masses all around this wheel like this. And for this thing, every single one of those masses is some set radius away. There's my mass 1 and my radius 1 away from the center. They're all set out there, right? But you can see how that would be different than, say, you know, a solid disk, which all of these pieces would be filled in with more masses at a different radius to the center of that mass, right? And so on and so forth. If I had a solid disk, I would have a very different kind of moment of inertia than I do for just a wheel. So it turns out that there are different factors of this, and you're going to have to look them up in a table. Anytime you want to use I, you've got to look it up in a table, because it matters how this thing rotates, where its center of mass is, okay, where its center of rotation is, and how it rotates. So for, and I need to look this up again, for this marker, if I were talking about this marker, it's basically a cylinder, right? If it were rotating about its center of mass right here, the pivot point was actually in the center like so, the I for that marker would actually be, and this is all derived from calculus, each one of these things, so we're not going to get into that, okay? But it would be 1/12 mr squared. So you still see that you have that mr squared in there. That still exists, okay? But you get another factor. You get a different factor for every shape. For a sphere, if I remember right, and I probably will be wrong on this, I think it's 5/2 mr squared. It's either 2/5 or 5/2. See, I forget all the time. So I use those tables like crazy. So you still have your I, okay? So your new formula, we're going to put it in there. I'm going to show you in a second. But just realize that I is going to be different for every kind of a shape you can talk about. If you're dealing with a cylinder rotating about its center, you've got this I for it. If it's a cylinder rotating about its end, it's going to be a different I. And I'll show you how to derive that too in my AP class, okay? So if you've got a disk, you know, if this thing were solid, right, you'd have, for a hollow disk, you'd have one I. For a solid disk, you'd have a different one. For a sphere, you get something altogether different. And it all depends on where it's rotating, right? Is it rotating about the center? Or is it rotating about somewhere on the edge, right? Is it rotating about that point? Those are very different I's, okay? So you'll look those up on a table, but finally, the thing you really need to get, okay? Final rotational kinetic energy formula is this. Rotational kinetic energy is equal to 1/2 your angular velocity squared times I. And that I, you're going to get that value for that particular object from a table, okay? And that is it. Put that in, you've got your rotational kinetic energy. In a little bit, I'll show you a video with my kiddos and we will have a race and see which object will actually make it to the bottom first. All right.